In the last class, we have discussed about the connection schemes of primary AC distribution system. In today's class, we will discuss about the secondary AC distribution system in detail. Okay. So, in the previous lectures, we have already seen the single line diagram of a sample secondary AC distribution system. Okay. So, the secondary AC distribution system starts with 11 kV bar 400 volt step down transformer. Okay. So, the secondary side of this step down transformer is star connected. So, because it is star connected, we have 3 lines or 3 phases and 1 neutral wire. Okay. So, we have line voltage of 400 volt and phase voltage of 230 volt AC. 3 phase 400 volt or single phase 230 volt. Okay. And normal residential loads will use a single phase 230 volt. That is, the load will be connected between any one of these 3 phases with respect to the neutral. Okay. So, if you look onto this diagram, this residential loads are getting connected to any one of the phases as well as the neutral. So, it is called a single phase 2 wire system. Okay, single phase 2 wire system. The 2 wires are R and N or Y and N or B and N. Okay. So, also in the secondary AC distribution side, we have 3 phase load which draws 400 volt. Okay. So, this 3 phase load uses all the 3 wires R, Y, B as well as the neutral. Okay. So, this forms a 3 phase 4 wire system. Okay. So, basically in the secondary AC distribution system, we have 3 phase loads which uses 3 phase 4 wire connection, and we have residential house loads which uses single phase 2 wire connection. Okay. So, now let us go in detail about the single phase 2 wire AC system. So, we have one phase wire which can be R, Y or B and one neutral. And this is the reactance of the winding, okay, of the line. So, here we take Vm as the maximum voltage between the 2 conductors, phase and neutral. So, the RMS value of the voltage is nothing but Vm by root 2. And we define few parameters: P, power transmitted; L, distance over which the power is transmitted; load power factor is taken as cos phi. Okay. So, we know the power transmitted single phase power P is equal to Vrms Irms into cos phi. Substitute for Vrms, which is Vm by root 2. Okay. So, after substituting, you obtain the expression for Irms. Irms is equal to root 2 into power divided by Vm into cos phi. And line losses, W is equal to 2I square R. So, I square R is nothing but the losses which occurs in the transmission line. So, we have 2 conductors. One is phase conductor, one is neutral conductor. So, we take 2 into I square R, where I is nothing but the RMS value of the current. Now, from this equation, you substitute for Irms. When you substitute, you will get 2 into root 2 P by Vm cos phi the whole square into the formula for resistance, which is rho L by A, where A is the cross-sectional area of the conductor, rho is the resistivity of the conductor material, and L is the distance over which the power is to be transmitted. Okay. So, write the expression for single phase power, where V and I represents the RMS value. Substitute Vrms as Vm by root 2, then get the equation for Irms. Okay. Then substitute Irms expression in the line losses. So, line losses general formula is I square R. Since we have 2 conductors P and N, it is 2 into I square R. So, on substituting Irms as well as the formula for R, we get this line. Okay. So, now what is root 2 square? 2. 2 P square by Vm square cos square phi. Okay. So, we will get the losses W. Okay. W is equal to 4 P square rho L divided by Vm square cos square phi into A. So from this, take the cross-sectional area of the conductor. Okay. So volume of conductor material is nothing but 2 into A into L, where A is the cross-section, L is the length of the conductor. So we have two conductors, one is phase, one is neutral. So volume of both the conductors are two-wire system. So two conductors, 2 into A into L. So from this equation, substitute for A. Okay. So then you will get 2 into 4p square rho L square by Vm square cos square phi into W. Okay. So now we are doing some rearrangement. That is cos square 2 divided by cos square phi term we are separating. 2 by cos square phi we are separating, and remaining all constants 4p square rho L square divided by Vm square W, we are considering it as K. Okay. So in the case of a single phase two-wire system, the volume of conductor material is 2 by cos square phi into K. Okay. So where K is this 4p square rho L square by Vm square into losses. Okay. But for a two-wire DC system, okay, volume of conductor is nothing but K. Okay. So we have, it's a known expression for two-wire DC system. We have the volume of conductor as K. Okay. So because we have the expression for K, we are trying to write the volume of conductor in the case of a single phase two-wire AC system also in terms of K. Okay. So now what conclusion we can make is the volume of conductor material required in a single phase two-wire AC system is 2 by cos square phi times the volume of conductor in a two-wire DC system. Okay. So for a single phase two-wire system, the conductor volume required is 2 by cos square phi times that required for a two-wire DC system. Okay. So in the same way, we are going to compare the volume of conductor in three-phase four-wire system with respect to a two-wire DC system. Okay. So the next derivation is finding out the volume of conductor in three-phase four-wire system. Okay. So coming to the three-phase four-wire system, this is the diagram for circuit diagram for that. We have three phases R, Y and B. So we will obtain a four-wire system only if the system is star connected. Okay. So from the star point, we have the neutral wire. Okay. So the current direction in all the three lines or phases are shown outwards. Okay. That means this is a three-phase supply. Okay. So I, in Y also I, B also Y. The magnitudes are shown like this. Okay. And the current, return current through the neutral wire is taken as IN. Okay. So now, if we consider the system to be a balanced system, it can be either a load or a supply. So in the case of a supply, the current will leave the three-phase system. In the case of a three-phase load, the current will enter the system. Okay. So if the system is balanced, the current through the neutral wire will be equal to 0. Okay. So for a balanced system, the neutral current will be equal to 0. Okay. So you know about KCL. What is KCL? The sum of currents at any junction is equal to 0. Okay. So accordingly, at this neutral node, the summation of currents will be equal to 0. So we will get IN is equal to I plus I plus I. This three are the magnitudes. Okay. So for a balanced system, all the three currents will be having the same magnitude, but they will differ from each other by 120 degree. So IR will be the reference, IY will be IR angle minus 120 and IB will be IR angle minus 240. Okay. So when you add IR plus IY plus IB, you will get it as 0. So this is valid only for a balanced system. Okay. But if you apply KCL at this node, the incoming current will be equal to outgoing current. What is the incoming current? IN. What are the outgoing currents? IR plus IY by IB. So for a balanced system, IR plus IY plus IB will be equal to 0. So IN will also be equal to 0. Okay. So because the neutral current in a balanced system is 0, the cross section of the neutral wire will be usually taken as half the cross section of the line conductors. Okay. So for a balanced system, since the neutral current will be equal to 0, the cross section of the neutral wire will be taken, usually it will be half that of the line conductors. Okay. Now defining the similar parameters, we write the expression for three-phase power P as 3 into Vrms Irms cos phi. 3 because it is three-phase system. Substitute for Vrms as V maximum Vm by root 2. Then write down the expression for Irms, root 2 P by 3 Vm cos phi. So after getting the expression for RMS value of the current, you have to write the line loss equation. So line losses W is equal to 3 into I square R. 3 I square R because we have R, Y and B lines, 3 lines. That's why 3 into IRMS square into R. Okay. And for a balanced current, for a balanced system, there is no current through the neutral wire. That's why we didn't consider the neutral wire here for calculating the losses. Substitute for IRMS, take the square, okay, you will get the losses. Then write cross-sectional area in terms of losses, okay. So after that, find out the volume of the conductor. So volume of conductor is equal to 3.5 into A into L. A into L is the volume of one conductor. So we have 3 line conductors R, Y, B, which is 3 into AL, and we have one neutral wire whose cross section is half that of the line conductors. So that's why we have taken it as 3.5 A into L. Okay. Now substitute for A. Okay. So our aim is to compare the volume with respect to the volume of a 2-wire DC system. So we are trying to get the expression for expression in terms of K. Okay. So what is K? K is 4P square rho L square by Vm square omega. So here we couldn't find 4. So what we are doing is we are multiplying and dividing by 4 to bring in the form of K. Okay. So multiply and divide by 4. Then we are doing some rearrangement. So 3.5 into 2 is 7. So keep this numerator 4 separately and separate the denominator 4. So 3 into 4 is 12 and bring the cos square phi also separately. So you will get 7 by 12 cos square phi into 4P square rho L square by Vm square W. So that term is nothing but K. So we will get the volume of conductor in a 3-phase 4-wire AC system is 7 by 12 cos square phi times the volume of a 2-wire DC system. Okay. So single phase, a 2-wire and 3-phase 4-wire are the normal connections used in the secondary AC distribution side. Okay. So now one more topic, effect of disconnection of neutral in a 3-phase system. So effect of disconnection of neutral in a 3-phase 4-wire AC system. Okay. So we know the neutral wire is connected to the neutral point of the distribution transformer. So what is the distribution transformer? Refer back to the diagram whatever we have drawn in the secondary AC distribution system. So this is the 11 kV bar 400 volt distribution transformer. So they have we have the neutral wire in the secondary side of the distribution transformer. Okay. So as I told, by considering KCL as the neutral, KCL at the neutral point, you will get IN, neutral current is equal to summation of the currents flowing through 3 phases, IR plus IY by plus IB. So for a balanced system, IR plus IY plus IB will be equal to 0. So IN will be equal to 0. Okay. So if the load is unbalanced, the current flows through the neutral to the ground. So that is the purpose of having the neutral wire. Okay. So for balanced system, nothing to worry about the neutral wire because neutral current will not flow. But all the situation, we cannot expect the system to be a perfect balanced one because there could be some load variations, there could be some supply variations, there could be some fault occurrence also. In that case, the system may go unbalanced. So when the system is going unbalanced, there will be a certain value for the neutral current. So that unbalanced fault currents should be diverted safely to the ground through the neutral. Okay. So in that case, if there is no neutral, what will happen to the system? Okay. So if neutral is disconnected, we call that situation as floating neutral. Okay. So in case of floating neutral, what will happen? The current which enters through one line will leave through the other two lines. Okay. So if there is a neutral, the unbalanced currents will go through the neutral and safely bypass to the ground. But in the case, if the neutral is disconnected, if there is no neutral connection, that current, extra current will also flow in the other two phases, which will cause overcurrent. Okay. So this is the diagrammatic representation in case if the neutral is disconnected. R, Y, B. Okay. There are three loads: R load, Y load, B load. Okay. R load is getting connected to R phase as well as the neutral. So this is the neutral wire which is opened now. Okay. So we are going to discuss what will happen if the neutral is disconnected, kept open. Then Y load is connected between Y phase as well as the neutral. B load is connected between the B phase as well as the neutral. Okay. So now see here, the current which is coming out of the R, the current which leaves the R phase is entering the R load. Okay. It's taking the path like this. Then again it enters the Y load. Again it's coming over here. Similarly, part of this current may come down. It is going to the B line also. Okay. So R, the current which leaves the R is entering back through B phase and Y phase respectively. Okay. So that is the current, instead of getting diverted, the unbalanced currents, instead of getting diverted to the neutral, it's going to the other two phases, causing extra current, extra load in the remaining two phases. So what are the side effects of neutral disconnection? Okay. So the potential of the neutral point always changes. Okay. So if there is no neutral, the potential at the neutral point always changes, and sometimes it may go up to 430 volt. Okay. And if the neutral is not connected to the ground, the system will experience large changes in currents as well as the phase voltage. Okay. And sometimes the load also may get damaged because of overcurrent. Why? What will happen? What will lead to the overcurrent? Because the current which is leaving one phase will enter through the other two phases. Okay. So dangerously high currents. Okay. So in this situation, sometimes it may lead to electric shock if we touch the equipment case.